Welcome to solverfy.
We are asked to consider the two compounds that I have listed at the top of this page. First, dichloromethane, and second, methyl iodide. We're given a table. Actually, I'm going to do the table. We're going to have our T and our T for first our CH2Cl2 and second our CH3I. I'm going to put my temperatures in here. My first temperature is negative 43.3. These are all in degrees C. These are data that are given in the problem. And our vapor pressure depending on the book that you're looking at, will be given in kilopascal, or is it Pascal? Yeah, kilopascal or torr. And I'm going to put the kilopascals in first. Or no, I lied. I'm going to put my torr in first. Kilopascals first. And then, these are the same pressures, but they're just going to be given in different units. This is 10.0 torr, 40 torr, same pressures, same temperatures, just different units. And whatever version you're using, I'm going to just be doing my calculations on this one with the torr. It wouldn't matter. You're not going to get the exact same numbers, but you get the same slopes and everything else. But I'm not only going to do one. We get to the later questions. Okay, question A says, which of these two substances is expected to have the greater dipole-dipole? And while these have very similar makeup, let me go to a different color for the answer. Each is going to be, if you will, an unsymmetrical tetrahedron with a single central carbon atom. Let me sketch them real quick. Okay, so these are very similar. We would, since the structures are similar, the magnitudes of the dipoles should be similar. And if we look up the dipole moments, which I saw somebody did, our dipole moments are for the CH2Cl 1.60 dBs and the CH3I 1.62, and that's very close. We're going to take a look at which one has the greater dipole, and that will be the Cl, because Cl is more electronegative. So the CH2Cl2 will have the greater dipole. But they're going to be very similar. The next part of this question says which has the greater dispersion. dispersion force. And that will be the one with the greater molar mass. Which will be the CH3I. That will have the greater dispersion force. And then finally, we're asked to specify or say, why is it difficult to tell? Which is more volatile? And of course, it's difficult to predict because they have very similar structure. The intermolecular forces are similar. Their dipole moments are similar. They're similar in so many respects that it's difficult to predict which one will have a higher volatility or which one will have the greater boiling point. Which brings me to part B. For part B, I'm going to go get a little brighter color. For part B, which compound would we expect to have the higher boiling point? And as we said, it would be hard to really predict. I cheated and looked them up, and the CH2Cl2 has a boiling point of 40.0 degrees C, and the CH3I has a boiling point of 42.4 degrees C. Let's go back to the table. If we take a look at our boiling points, we see that each one of these is a smidge higher than the boiling point, or excuse me, is a smidge higher than the temperature for the same vapor pressure. So just based on that, I'd expect this one to have the higher boiling point, and it does. Okay, now let's go to part C. Part C, the order of volatility of the two substances changes as the temperature is increased. phenom, and I always spelled that word wrong. Phenom and non. Okay, did I get that written down correctly? The order of volatility changes as the temperature increases. That means that they're actually going to sort of switch, if you will. I'm going to go to the next page. Let's go to this. We know that a plot of the natural log of p versus 1 over k, and remember k was the same, is linear. And if the volatility switches, which is more volatile, we're going to have the two lines that we would get will be similar, but there will be a crossover point Now it's not going to be nearly this big. So I'm just going to make a pretend crossover point, and then we'll actually look at these. So I might have one that looks like that. And then I might have one that's a little bit different. Let's just make a different color here. That looks like that. And this is what I'm talking about. We'd have a different crotch. And that would mean that I had a different y-intercept, and there'd be a crossover. And that's what we're going to be looking at. I can't believe I forgot to put my pictures in here, and I'm not going to start this over. So I sent myself some pictures, and then I forgot to download. I'm not going to pull that up. But our I entered the following data into the calculator. I did the data that I'm going to highlight in pink. I did the temperatures. I did 1 over k for those temperatures, and I used these. For the second set, I did these, and again, I'll put them underneath. I used these. So my natural logarithm of which is my y-axis stayed the same. So I'm just going to write down the points I did, and then we'll work from there. So I did 2 sets of points. The ln of p was the same for each. For both trials, for both substances, I had 2.303, 3.689, 4.605, and 5.991. Then, that's going to be the same for each. My Kelvin temperatures, those will be my CH2, CL2 data. My Kelvin temperatures were 229.9, 250.9, 266.9, and 297.9. And my 1 over k are 4.351, times 10 to the minus third. Each of these is times 10 to the minus third. Okay, I sort of got ahead of myself. My answer was for part C was the lines have to cross. I am now answering part D. This is part D, where we are going to prove what we just said. And part C says what quantity must be different. So I'm going to put that answer right here. What must be different would be my y-intercept and my slope. My y-intercept and my slope must be different, and my slope will be my heat of vaporization. Okay. Now, let's switch colors again. And now for my other compound, we're going to prove what we just said. My Kelvin temperatures for this one will be 227.4, 249.0, 266.2, 298.5, and now my 1 over K will be 4.398. Okay, and I'm going to make two plots here on the same graph because they're very similar. My first plot will be these two sets of data, and my second plot will be these two sets of data. So you'll see that my y is going to be the same. I'm going to have the same values on my y. That's going to change will be my x. So what I did is I put these sets of data into my graphing calculator. And I'm just going to pull up my calculator here and tell you what my slopes were, because I forgot to write these down, or I forgot to send them to myself. So for my first set, this one right here, let me change colors. For my slope, I had negative 3744.5. And my y-intercept was 18.60. So the equation for my line was y equals negative 3744.5x plus 18.60. For my next equation, when I entered these values into the calculator, I ended up with negative 3520.5, and I gotta go look this one up. Um, 17.81. So the equation for my line would be this. I'm going to write this a little bit smaller so it fits. Okay. So we saw that we did have a different slope, and then I'm going to figure out my heat of vaporization. For my first one, for my CH2Cl2, My heat of vaporization will equal my negative slope times 8.314. And then I'm going to convert that to kilojoules. So I'm going to divide it by 1,000. And that will be negative 3744.5. Take the negative of that times 8.314. And I should do joules. And this is joules. Over. That's not joules right there. There we go. And when I'm done with this one, I got 31.1 kilojoules per mole. So that's that value. And we saw that our y-intercept again was 18.606. And for my other substance, my heat of vaporization is going to again equal the same calculation. So I get 3520.5 times 8.314. And for this one, I got 29.3 kilojoules per mole, which was a different heat of vaporization. So I think that's all I really needed to do here, because that did prove that we have different slopes. If we have different slopes, thus they will have a crossing point. I think that's all we have to do. Finally, we're done.